And yes, we are live with another episode of the OpenStack online meetup. Today with us is Wim. He will talk about how to turn OpenStack Swift into a VM storage platform. And so Tim, with that said, let me hand over to you. Just a few logistics front up for all those of you who have questions during Wim's presentation. Feel free to do that either through IRC. We are on Freenode and OpenStack #community. You can also ask via Twitter at OpenStack_OM, or alternatively, you can send me an email. So the email address is on the bottom of your screen. And now with that said, let me hand over to Wim. Wim, the stage is yours.
Hi, thank you, Raphael. Hello, let me first start by sharing my screen. I hope that should be it. So hi, I'm Wim Provost, and I'm a product manager for vStorage. And we are here today to talk about turning OpenStack Swift into a VM storage platform. So I'm a product manager for vStorage, and vStorage is part of CloudFounders. And CloudFounders, who is that? Well, most of the people will not have heard about CloudFounders because most of the time we do OEM deals. And the persons that heard of us, well, most of the time they make a bad joke. Something like, hey, I didn't know you lost the cloud and you found it. So that's kind of the thing we do. And we are with 120 people in the US, Belgium, Romania, and India. In the US, we most of the time do sales. In Belgium, we do the core development. And in Romania and India, we have QA and also development. Now, CloudFounders is really a company that founds clouds, that creates clouds. So we create private and public clouds. And we have two product lines. The first one is vStorage. That's what we're going to discuss today. And it's an open source project, and it's licensed under Apache 2.0. And it's, in short, it creates an ultra reliable, high performance open storage layer for virtual machines. It's compatible with all major hypervisors, and of course we have OpenStack support. That's basically why we are here. Now, the reason why we created vStorage is we also have a second product line, which is vRun, which is converged infrastructure. So that means that we go from the bottom until the top, so we do the whole stack. It means that we start with hardware, we put software on top, we put support on top, we put updates on top. So it's a whole package, and we sell that to customers that are interested in a private or a public cloud. And while we were doing that, because that was the product we first did, we got a lot of questions from people that only wanted the software layer or the storage layer. And we get that question so many times that we said, okay, it's now really growing, the storage market, so let's do something with it. And we took the core technology from our converged infrastructure, and we turned that into vStorage. So vStorage is basically a technical technology spin off from vRun. And what is vRun? Well, it's software that transforms server hardware, x86 hardware, into a private or a converged infrastructure with, of course, lots of performance, flexibility, scalability, things like that. And it uses vStorage as a basis, and we use it to compete with the likes like Nutanix, SimpliVity, or Evorail. So we built on top of an OpenStack, we built a converged infrastructure on top of OpenStack with vStorage as the core technology for the storage software. So that's so far for the marketing of what we do with CloudFounders. So let's talk business. First of all, I think everybody here is aware that object storage is really the future if you want to build scale-out storage. If you look at the amount of storage that's being generated these days, well, you can't fit it anymore on a single hard disk, on a single server, so you really need to have a scale-out storage system. If you see at what's currently at the market and what everybody is predicting as the future for scale-out storage, well, there's only one way to go, and that's object storage. So object storage is really the future if you want to store massive amounts of data. And Swift, which is an object storage, which is in OpenStack, well, that's one of the things that you can choose. Now, what is the advantages of using object storage like Swift? Well, it allows you to build scale-out storage by just adding more disks, more nodes when you need it. You don't have to think in advance how much storage you will need. No, you can just plug in a disk. You can plug it more servers when the need for storage is really there. It's also very highly reliable. Because the way these object storages are built is they use a zero-share architecture, which means that things can fail. They are really built so that a node can fail, a disk can fail. So you shouldn't be worried about that, and that keeps it highly reliable. And by using a distributed nature, you just don't have any downtime anymore if like one node goes down or one disk goes down. So that's a really big advantage. It's easy to manage. In the past, you need to know about sums, you need about rates or volumes. Now you just store objects. You just do a put and a get. That's the basic actions that you can do with an object store. So it's very easy to use for adding data or getting data back out of the system. And Amazon really did a good work there, because there's now almost a standard API. Because Amazon S3 is by definition almost the API that you need to support in case you want to have a successful object storage, which means that there's no vendor lock anymore. If you would have a Sun or traditional NAS, well, these are silos, and if you want to move from one vendor to another vendor, that's kind of almost impossible. Now with these standard APIs, you have no problem with that. And object storage is also very cost effective, because you want to store massive amount of data. You will want to use very large capacity SATA disks. These are very low cost, or these are low cost, but these have a great capacity. Only recently, Western Digital announced 10 terabyte disks. Seagate has 8 terabyte disks, so you have a lot of capacity on disks. And although these disks are a little bit slow, and you can easily also increase the performance of the object storage in most cases by just adding more spindles, so adding more disks, because then the load of the storage will get spread across multiple spindles, across multiple disks. Or if you're using a gateway in front of the storage system, you can just add more gateways, and that means that you have more interfaces, so you have more options to put gets and puts and things like that. Now, I've been saying here that object storage is really the future for storing massive amounts of data. Now, there's one technology which creates massive amounts of data, and that's virtual machines. There's only one problem with it, and that's virtual machines are not really working at the moment with object storage. Now, why is that? Well, there's a couple of problems if you want to use an object storage like Swift as a virtual machine storage. I'll first start with the most difficult one. That's called eventual consistency. Now, what is eventual consistency? In case you build a distributed system, and these object storages are distributed systems, you are bound by the cap theorem. It's like the gravity force that we have here on Earth. It's kind of the same thing. You cannot escape from it. So what is it? In case you build object storage, or in case you build a storage platform, or in case you build a distributed platform, there's three things that are important. First of all, you have consistency, which means that if you store something on the object store and you want to get it back, well, you want to be sure that you get the right data back. The second thing is availability. If you have a storage system, you want it to be available. And if you build a distributed storage system, then you have partition tolerance, which means that if some part of that system goes down, you still want to be able to survive that. Now, there are three things that are competing with each other. You cannot have all of them at once. That's a theorem which is existing in the distributed IT architecture, and so far nobody has found the holy grail to create something which is consistent, available, partition tolerance, and very performant. So there's no way around that. That's kind of a thing that you have to accept. So what, for example, Swift has done, they have said, okay, we want to be always available. We want to tolerate failures of some part of the storage. So that means that we have to trade up something, we have to give up something, and we will give up consistency. And consistency means, yeah, they'll have to go to eventual consistency. So what is eventual consistency? And so what is the problem with Swift? If you store something on Swift, and you do, for example, an update on Swift of that object, there is no guarantee that you will get the last object back, so the last written object back. It could be that you get the previous version. The reason for that is you have multiple interfaces, and you could store something on the first interface, and if you get it back, you could ask it from the second interface. But to make sure that it's performant enough, they don't copy the data, or they don't copy the metadata from one node to the other node, so that it's fast enough. So they sacrificed consistency. So with a Swift, if you put something on it, you're not sure that you will get it back. Now think about hypervisors. If a hypervisor requires a block, well, it expects it to be the correct block. It expects it to be the correct data. Virtual machines cannot cope with data which might be correct or might not be correct. So that's already a big problem for object storage like Swift. Now, the second problem that you have as an object storage is latency and performance. Virtual machines are very, they really require performance storage, and they really require low latency for their disk access. Now, that's really a problem, because object stores are not built for latency and performance. They are built for storing massive amounts of data, and they do that typically because it's slow technology. They use large disks to store that data. So they use slow disks to store that data. So there's kind of a mismatch between virtual machines requiring high speed, high performance, low latency disk access, and object storage, which is offering only a low performance, or not high performance, and a high latency. Now, the latency is even additionally or multiplied, because the object storage is on a LAN, or in the network, and not really attached to the server itself. So if you have a server with disks inside, your virtual machine can talk directly to those disks, and it will be very fast. Now, if it has to go over the network, well, you've got some latency, you've got some overhead of the network, so it just becomes slower. So latency and performance offered by the object storage is also a problem. And then, of course, we have the different technologies. If you see object stores, well, they speak objects. You can do puts and gets of objects, while hypervisors, they use blocks or even files if needed, but they have been adjusted to blocks, to work with blocks. Now, that's like cats and dogs. They don't understand each other. So there's really a problem. You cannot just take Swift and VMware and make those two, or KVM, and make those two talk to each other. So what is needed? There's a technology needed which understands on one side object stores, and on the other side understands hypervisors, and it needs to create a technology so for virtual machines, so that they can use object stores like a SAN, and they still get the benefits of the low-cost storage and the scale-out of the object storage at the same time. So that's really what we're looking for in the future for making sure object storage can work as virtual machine storage. Now, let's see how we do a traditional OpenStack setup. Well, if you have already Swift installed, you can store Swift. You can use Swift to store your images, for example. And if you create a new Nova instance, you will use Cinder for block storage, and you will take a glance image to create that virtual machine. And if you take a backup, for example, of that virtual machine, Cinder will make sure that it gets stored in Swift as an object storage. Now, lots of people have this setup, and what they do is they try to use Cinder for the virtual machines. Now, very quickly they will run into issues, because if you use local storage, well, that's not going to work. If you use something else, it's just going to be a management nightmare with iSCSI targets, and it's not going to work. So the next step is what people do is they add a distributed file system or a distributed storage platform underneath, so they can use Cinder to use that Ceph or Sun or NAS and provide disk space for that virtual machine. But in that case, it works, of course. It's a setup that people are using, but that means that you're really maintaining two storage platforms. You have Swift for your object storage, and you have Ceph for your block storage. So that really doesn't make sense. So if you're OpenStack and if you're OpenStack minded and if you really want to use OpenStack for the maximum or at its best, so there's only one thing that you really would want, and that's using Swift, the object storage, to run your virtual machines. So this is exactly what vStorage allows you to do. So you have Nova. This provisions the VM. You have Cinder, and as soon as a volume is created on Cinder on the block storage, it will talk to the vStorage API, and that vStorage software will provide disk space on Swift for that virtual machine. So it's really tied together. So you create through the Cinder API, for example, a volume, and it will end up in Swift, and you can use it. The virtual machine will not even know that it's running on Swift. It will just think it's running on a shared storage platform or on a NAS or something like that. So it's really a very nice integration that we've done there. Now, I've already introduced vStorage, but what is it exactly? It's an open source storage router. So that's how we call it. That's how we label it. We've really searched very long time to find a good definition, because it's kind of a unique thing. We're kind of on our own with this. And what it does is it's installed on a host or a cluster of hosts to create a storage platform that is VM-centric, clustered, reliable. It can scale out, it's high performant, and it's only for virtual machines. So that's kind of what we do. Now, why did we invent the term storage router? Well, if you see what vStorage does, you can compare it with a distribution center of Walmart. So if you would go to Walmart and you buy an item in Walmart, then you're not the store, the Walmart where you buy that item. It will not receive that item straight from the manufacturer. So Walmart has a distribution center in between that chain. So the guy that produces the item will send it to the distribution center. The distribution center can do some clever things with it, like chop it up in parcels, make sure that it's the right amount, and then they send it to the end shops. So that's kind of the same thing that we do. We take in data from the virtual machines, we can chop it up, we can do things with it, we can create snapshots on it, and then we can store it to the storage backend. So we are kind of a virtual machine router, a virtual machine storage router, a distribution center for virtual machine storage. So that's kind of what we do with vStorage. To make it a little bit more concrete, you have vStorage that runs on the hypervisor, but what does it do? Well, first of all, it gives you a great performance, because we will use the SSDs inside the hypervisor, or even PCI flash cards inside the hypervisor, and that means that you can get a very good performance. We have even seen more than 40,000 IOPS per hypervisor, so you get really performant storage. The second thing is it's only made for virtual machines, so we are not an NFS gateway. People sometimes mistake us for that and want to use us as an NFS share to store data or to store files on an object storage. We're not that. We only take care of virtual machines. We only accelerate virtual machine volumes. We also have a unified namespace, which means that if you have multiple hosts, you can create one big namespace. You can create one big file system across all those hosts, a little bit like a distributed file system. And this means that you can do things like vMotion or live migration or evacuate or things like that. It's ultra reliable. This means we use a zero shared architecture, and it means that if something goes down, you can just boot it up, something else will take it over. It's really the future of how to build distributed systems, this zero shared architecture. It's not an active passive or an active active. No, everything can just take over the role of another component. One more enterprise or enterprise feature or feature that you normally get only with with Enterprise Sense, or for example unlimited snapshots, which means you can just take snapshots all you want. It's zero copy snapshots, so it's very lightweight to take another snapshot. It's endlessly scalable. It's scalable in more than one way. You can add more storage to the Swift backend, for example, in case you use Swift as a distributed file system, as an object store. So that's scalable. So it's scalable in capacity-wise, but it's also scalable in performance-wise. If you want to add more performance, you just add more SSDs or more PCI flash cards to the hypervisor, and all of a sudden you just have a much more faster or a much more performing storage system. And we've also made sure that we decouple the capacity or the RAM capacity or the CPU capacity from the storage, unlike you have, for example, with hyperconverged storage appliances where the RAM and the CPU and the storage are combined. Here you can just scale RAM and CPU if you want, or you can scale the performance if you want by adding more SSDs, or if you want more storage capacity, you just add more disks or more nodes to your Swift cluster. So as a backend, what can you use? Well, you can use a Sun or a NAS. You can use object-based storage, which is, of course, the future. Or if you want, you can also use the distributed file system, but that's more the choices that you can have. So how does it look really in reality? Well, first of all, you have your KVM hosts. That has the virtual machines. And you need to configure your KVM so it creates its .raw files inside a virtual file system interface, inside a virtual file system. And that file system, that gets spread across all the nodes. So all the nodes see the same virtual file system, and that virtual file system is per storage backend. So a backend for us is, for example, a Swift. If you have one Swift cluster, that's one backend. If you would have storage policies, for example, you could have one cluster or one environment or one pool with a high protection level and one with a lower protection level. For example, one is with critical data, the other one is with test data. You could create that into two pools on Swift, and then you could add that as two virtual file systems into your KVM, so that you can select, okay, where do I want my virtual machine to have its .raw file saved. And as soon as that .raw file is saved, OpenStack will notice that, and it will put it onto Swift. It will do some things with it, but it will end up in Swift as a bucket. Now, you also see the SSDs, which are next to the vStorage. Every host which has SSDs, from that host we will take the SSDs and we'll use them as a read cache and a write cache, just to make sure that you've got the performance needed and the latency, low latency for virtual machines. So caching is happening in the host, and this is very important because if you do caching already on the LAN or on another node, then that's not going to work. The latency will be way too much, will be way too high, so that's not really what you want. You want, and this is something that you see, for example, with the new hyper-converged appliances, caching is there happening as close to the CPU as possible. So this is really the future. Now, it's a scale-out architecture, so if you have one KVM node, you can add a second KVM node. You can just make sure that the virtual file system gets spread across all those nodes. And this means that, of course, as all the KVM nodes are seeing the same virtual file system, they see a kind of like a NAS. They can just do, or they think that they see shared storage, and they can just do vMotion of live migration or an evacuate of one VM from one node to the other node. So that's all possible. And once the data is no longer needed inside the SSD or inside the caching layer, then we push it down to Swift to be archived as kind of a cold storage, like you would have that with two-tiered storage. Now, how do we? Well, there was a question on the forum. How do you see blocks and how do you see objects being working together? So where is the magic happening? Well, this slide is explaining how we do the magic, or where the magic is happening, and it also solves one of the biggest problems you would have with Swift using it as an object storage or for a virtual machine platform, and that's the eventual consistency. So eventual consistency, again, is if you store something on Swift, you're not sure that you get the right version back. So most of the time it will happen that you get the right version, but it might be that if a node fails or a disk has failed, that you get an old version back. So that's kind of what eventual consistency is all about. So how do we turn blocks into objects? Well, I have here a virtual machine that's doing writes. So it's doing the writes from LBA1, 4K block, LBA2, a 4K block, LBA3, a 4K block. So you see all the LBAs, so the addresses inside the virtual machine that are being written. So we are now at the virtual machine level. And you see, as time goes by, you can see that the new writes are being coming in. Let's put it like that. So what we do is we kind of append these writes to a log, to a storage container. It's a kind of a log-based approach. And as soon as we have enough blocks inside the storage container, inside the log, we close that log and we push it down to the storage backend. So this is where the magic happens. So on the SSD, we're still using blocks. We also use we use those block storage, or we use that block storage technology to create the storage containers, and once storage containers are full, we push them down to the storage backend. And typically that's a 4 megabytes storage container. Of course, it can be smaller. For example, if you do a snapshot, then we close the storage container much faster. So on the SSD or the PCI flash card, you are still using blocks. You can just address it like it would be blocks, because the LBAs, you can just reference to an LBA and it will get the block from the scope. On the back end, we don't have that anymore. So on the back end, we don't use, for example, a metadata anymore. On the back end, you just have a collection of items that were written. And if you would see a scope, the scope is just a collection of data writes to a virtual machine, one after another. So if you would, all the data is still there, so it's great for doing snapshots and for having history, because we always have all the history. We have all the writes that have been done to that volume. Of course, it would be slow if you would do that on the front end on the SSDs or PCI flash cards. So there you really have you really need that location-based storage approach, that block-based storage approach. Now, how does this solve eventual consistency? Well, as said, we use an append-only technology. So you only do appends to the log, to the storage container, which means that if you overwrite an LBA, you just add it to the log. You will not update that LBA number or something like that. You would just add that write to the log, to the storage container. So in a storage container, it might be that you overwrite like 4 or 5 times the same LBA, but that's not a problem. And then you push it down to the backend, to the storage container, to the backend, and there it rests. And if you need data back from the storage container on the backend because it's no longer in the cache, you have 2 options. You call the scope and Swift says, okay, I don't have it. Or Swift says, okay, I have it. Remember, we only do we don't do overwrites, so we only write a score once. So every object that's been put to Swift, it's only been added once. It's not been overwritten. So you don't have object versions. You only have new scores coming in. So if the score is on the backend, you just get it back. If for some reason Swift says I don't have the score, you can just wait a little bit. And as Swift is eventual consistency, so eventual, all the nodes will see that the new data is there. You will definitely have that score back. So you'll never have data loss or something like that, or you don't have an issue anymore with scores not being there or something like that. Okay, now Open vStorage and distributed file systems. What a lot of people think is that we are a distributed file system. So let's make this very clear. We are not a distributed file system. We are not a new version of ClusterFS, for example, because what you do if you have, for example, if you want to build a distributed storage platform, or if you want to build a storage platform for virtual machines, what people typically will do is they will take a distributed file system like a ClusterFS, and they will spread it across all the KVM nodes, and the virtual machines will create their .raw files in that distributed file system. And as soon as that raw file is being created, it's being copied to all the different KVM nodes to make sure that every KVM node can see the same data, can access the same data. Now, this is not going to work if you're doing virtual machines. If you have virtual machines and you have to copy every bit of data that's been written to that distributed file system, that's never going to work. It's just going to be horribly slow. It will not be performing. Of course, it will be as it's distributed. It's high available, but it's not going to work. You can't be fast enough. Your technology will never be fast enough. Latency will be too big to spread all that data across all the nodes all the time. So we kind of realized that very soon, and we said, okay, Open vStorage, we're not going to build a new distributed file system. If you want a distributed file system, you can go to ClusterFS or anything else, ExtremeFS, and get it there. So please don't use us to store files across multiple nodes. Now, what we do is we are a storage platform for virtual machines. So what happens? You have your virtual machine, you create your .raw file in the virtual file system interface, so the virtual file system, so the VFS1 on KVM1. And as soon as you create a file there, the object router, which is a piece of technology inside Open vStorage, will analyze what kind of file it is. It will see if it is a volume file, if it is a real disk of a virtual machine, or if it is a configuration file or something else. So if it's not a virtual machine volume, if it's a virtual machine volume, it will treat that completely different. So it will take that raw file when it's created, and it will create a bucket on Swift for that virtual disk. So all the writes to that virtual machine's disk will happen, or all the storage containers, all the writes for that virtual machine will end up in storage container objects, which are pushed to that single bucket, vdisk1, on the storage backend. And of course, the storage backend that's shared across all the nodes, but we can discuss that later. Now, if it's an XML file or if it's just a config file of the virtual machine, that will be handled by a file driver, and that will chop up the XML if needed and store it into an internal bucket for the whole unified namespace across all the KVM nodes. So very important to see here is also that you have KVM1, KVM host 1, which has virtual file system 1. You have KVM2, which virtual file system 2, and KVM3 with virtual file system 3. Now, there is a reason why we have put virtual file system 1, 2, and 3, because if you would use a distributed file system, it would be always the same virtual file system. Now, what we do is we have separate instances of the virtual file system on every node. So the virtual file system on node 1 is different than the virtual file system on node 2 is different from the virtual file system on node 3. So these are completely separate instances. So it's not a distributed virtual file system. Let's make that clear. Now, the reason why we've created separate instances is this kind of makes sure that you don't have to copy all the data, because virtual file system 1 is the only one that really has access to volumes on the KVM node 1, or from config files of virtual machine 1, which is running on KVM host 1. Now, KVM 2, they can see, or KVM 2 and 3, they can see which volumes, which .raw files or which XML files are stored into the virtual file system, but they are not the owner of that volumes or of that XML files, because the volume is running on KVM1, and they can see it, but they can't do anything with it. So they cannot write to it, they cannot directly read from it, they can't do anything, they can just see that it's there. So the only thing we have to do to make sure that the virtual file systems are, or that the host, KVM host 1, KVM host 2, and KVM host 3 believe that it's the same virtual file system that they see kind of NAS, is we share or we distribute the metadata of that virtual file system across all the nodes. So it's very important to see that first, we are not a distributed file system, and two, and because we are not a distributed file system, because every host is having its own virtual file system, that means that you can be much more performing, because you don't have to replicate all the data across all the nodes. So first, we are not a distributed file system, and secondly, KVM host 1 is writing its data to virtual file system 1. You have the object router there, and that object router will say, I am the owner of the volumes of virtual machine 1, of all the virtual machines on KVM 1, and I'm the owner of all the XML files which are being written by KVM 1. So that's really great, because that means we've solved a problem with the performance of a distributed system. Now, of course, this is not really the complete solution, because you always want to have live motion available. So you want to be able to move your virtual machine from KVM host 1 to KVM host 2. And you want this to happen without having to do any downtime, without having to copy a lot of things. So what happens? In phase 1, your virtual machine will be moved by KVM, like you would have it with the normal hypervisor management tools. The virtual machine will be moved to the second KVM host. So it's being live on the second KVM host. It will start doing writes to the virtual file system on the second KVM host, and the object router underneath that virtual file system on the second KVM host will notice that it's not the owner of those of those volumes, of those config files of the virtual machine, and it will transfer all the requests to the object router on the KVM host 1. And then, of course, you're following the traditional path. Object router 1 on KVM host 1 is the owner, so he can access the storage backend, the buckets of the vdisk, for example, or the internal buckets to do something with the VMX. So you can override that VMX. But again, the object router on virtual file system 2 is not capable of doing anything like sending, like making changes to the volume, which of course makes sure that you don't have two hosts writing to the same volume at the same time. So that's another problem that we've solved. So you don't have corruption of that volume, for example. Now, of course, we are quite sure that this is not, or we know that this is not a situation that you can do that can be sustained. If you have to transfer all the read and write requests from one KVM host to another KVM host, that's going to be a problem in the end. So once the live motion is done and the threshold of I/O is being captured, or how do I say it? It's the threshold has been surpassed on the virtual file system 2. So you have more than X requests on the virtual file system 2. The object router on the KVM host 2 will talk to the object router on the KVM host 1, and they will kind of schedule a handover moment. So they will talk to each other and they will say, okay, let's do a handover from this point, and as soon as that handover is being accomplished, the volume will be owned by the KVM or by the object router on KVM host 2. So from then on, it's the object router on the host 2 which will take care of every write to the storage backend or changes to the configuration file. So at that point, it's really virtual file system or the object router on KVM 2 that's the owner, and object router 1 has nothing to do anymore with it. Now, of course, this isn't the case in case KVM host 1 and KVM host 2 are up, and object router 1 and object router 2 can talk to each other. Now, if one of the KVM host 1 is down, you can't, of course, negotiate anymore between a handover point, and then we will talk to the management framework. So in this case, it would be OpenStack to ask, okay, is the KVM host really down? And if it's really down, we allow to steal that volume, to steal those files from the object router. But that's only the case in case KVM host 1 is down. Then we know for sure that KVM 2 can take over that role as the owner of the volumes and the files. And we again know for sure that there's no possibility that two hosts will be writing at the same time to the same volume. So just to recap a little bit of what Open vStorage has done to solve as problems. So Open vStorage is a middleware layer. It's a layer in between the hypervisors and the object storage, and it converts the blocks needed by the hypervisor into objects on the backend. So on the host, we use a location-based storage. which is block based, so you can just go to an LBA and ask what the data is. While on the backend, so on Swift, we will use a time-based storage, so storage containers and 4 megabyte files, basically an appended kind of log of all the writes of a certain time, and that's of course ideal for object storage because it's big chunks. It's definitely files, it's objects, so you can really push that out. They're really made for doing that. So Open vStorage is really the technology that turns the volume into a single bucket on Swift. Now, second thing we've done is we've created an OpenStack Cinder plugin, which means you can do easy integrations with OpenStack. So you can just create a snapshot through Cinder, and it will take a snapshot of that virtual machine. So that's the second thing we did. Again, we are not a distributed file system. So because distributed file systems don't work for virtual machines. They're just way too slow. So we had to think about something different, and the thing we do is we trick all hosts in thinking they see the same virtual file system. So they really think they see a shared NAS platform or a shared file system. But actually, the volume is only live on one host instead of all hosts. So we don't have to copy all the data across all the hosts. We have the data live on one host, and when it's no longer needed inside the cache, we just push it down to the storage backend. Now, of course, we have the volume which is live on one host instead of all the hosts. Of course, if you write something to a host on the first host, we also create a copy on a second or a different host to make sure that if your first host goes down, you still have like a backup of that last written data which is not committed yet to the storage backend. And to get the speed up to speed, or it's kind of badly said, but we only have to distribute the metadata, so we only have to share the metadata across all the hosts. So the virtual file system meta is distributed across all hosts, and not all the data inside that virtual file system, which makes it again work because there's much less data to transfer across all the nodes. And to really fix the problem with the mismatch between the slow and high latency backend, being Swift, and the fast, low latency requirement of virtual machines, we use caching inside the host to make sure that if you write something, it's done on the SSD and it's immediately reflected to the virtual machine as a write, so you don't have to wait till it's up in the backend. And the reads, well, if you have a read cache on the SSD, you will first check if it's on the read cache. If it's not on the read cache, you only then you have to go to the storage backend, which is much slower. But that, of course, doesn't really happen a lot of time, because most of the time your caching just takes care of the data that you need. Now, the benefits. Well, first of all, you don't have to manage anymore two distributed storage platforms. So remember the slide where we had the OpenStack architecture with Nova, with Cinder, with Glance, and with Swift. Well, you don't have to manage a Sun or a NAS or Ceph anymore. You can just use Swift, use it to its maximum. It's a great technology. It's a great platform. It's very robust. It's being used by big names. You've got Disney. You've got PayPal is using it. You've got eBay using it. So that it's really a great technology, and it's very performant. And it's infinitely scalable. Almost, you can just add more nodes when you need to. So you have really a platform that's really great for doing this kind, for storing lots and lots of data. Now, of course, you want to have really good caching, and the only way to have caching which is good enough or if you want to have enough speed on your storage platform for virtual machines is when you do caching inside the host where the Nova instance runs. You don't want to do caching on a different node, or you don't want some algorithm to define where your caching or your objects are placed on another node. You only want to use really the caching which is inside the host of where the virtual machine runs. If you do it differently, it's not going to work. It's not going to be performant enough. So that's really the way forward, using caching inside hosts very close to where the virtual machine is running. It also brings VM-centric management on a storage level, which means that you can do thin cloning, zero-copy snapshots. You just can do all actions on a virtual machine level instead of going to a storage level where you would, for example, have to create a LUN or copy a LUN. That's no longer needed, or snapshot a LUN. That's no longer needed. You can just take a virtual machine. You can just click a button, and you have the virtual machine, which is being snapshotted or for example, thin cloned. And something which is less important for people who are using Swift, of course, but Open vStorage is capable of adding many backends. So that means, for example, if you have a storage backend which is not compatible with Cinder, you would just use Open vStorage to make that storage compatible with Cinder, just as a side note. Okay. Now, supported OpenStack actions, we've released our first version, and what you can do already the basic actions, so add, remove, create, delete snapshot, clone from snapshot, clone volumes from volume, import image to volume, export volume to image, and for example, on instances, you can do live migration, so move virtual machines live without downtime from one host to another host. That's possible on top of Swift. And you can do, for example, an evacuate if one of the hosts goes down. So that's all supported as OpenStack actions in our Cinder plugin. We also had a question about deployments. While this is still very new technology, I just noticed today that in 1 week we will be celebrating our first birthday. So it's all very new. So that means that we don't have any big deployments with customers like an eBay or like just name a big name that uses Swift. We only have our internal environments now, and these are all running Open vStorage plus Swift. Just eat your own dog food, I would say. And Open vStorage is at the moment available in a beta. We don't give commercial support. So if you would contact me after this presentation and would ask, hey, I want to have commercial support, we're not going to do it. The only thing that we say is feel free to use it in test environments and provide us feedback, just to make sure that it's hardened. That's why we also use it in our own internal environment. So we're using it inside our own environments to build large clusters for storage for our own public cloud offering. So feel free to use it in test environments. We haven't certified it, and the reason for that is you have to be well in advance before you can get it certified. There's a whole set of steps that need to happen before you can get your OpenStack Cinder plugin certified. We are down to that path, so we will officially turn in a request to be certified at the OpenStack conference in Paris, which means that by the next release we expect to be certified, which would be at the killer release. But everything works already, so that's not a problem. It's just that we don't have the official certified OpenStack Cinder plugin labeled yet. And if you want to give it a try, just do that. The only thing that we're really interested in now is getting the message out there that we exist, because that's very hard these days for an open source company, because there's a lot of big brands with lots of budgets who are shouting and trying to push you away. But we think that we've got something very good. It's open source. People will love it, and you can just use it as you want. And let's just make the agreement that if you use it as you want, that you get a supported production license in Q1 2015. So because then we will have a production ready version that we'll also be using to host other environments, to help people to set up environments. So that's when we really go to a market. Then we say it's rock solid. But of course, I would say feel free to use it in test environments and provide us feedback. If you're happy with what we do, or if you think that somebody is interested in what we're doing, just send them an email. Just drop an email and let them know that we exist. So what are the next steps? For those who are Python or feel comfortable with diving into code. It's open source, which means that the main thing is where the code is living. So bitbucket.org/openvstorage. This is where you can find the code of the OpenVStorage project. Now, if you just want to get a hands-on, you can download the packages and deploy it in your own OpenStack environment. It should be quite easy. We have, for example, Debian packages, so apt-get install OpenVStorage should get you already a long way. Now, if you want more information, we have the documentation website, which is doc.openvstorage.com, and of course we have a support group. We use Google Groups for that. And you can just register. We just require you to have to sign up for the support forum. It's completely free. We just like to keep track on who is using it and why you're using it, and to start a kind of dialogue, because that's one of the worst things if you have open source software. Everybody's using it, but you don't hear anything about it if it's working great. It's only when you hear when it's not working great that you hear problems. And so that's why we say if you're using it, just register so that we can start communicating about how you're using it, what you're doing differently than we are doing it. Because, yeah, it's open source is really about communities, about doing things together, about sharing your views, and that's why we have the Google groups going. Of course, you can also follow us on Twitter. We've got @OpenVStorage, or you can read our blog, blog.openvstorage.com. Our blog is focused on technology. So, for example, the whole live migration thing, that's being explained on our blog in much detail. We also explained, for example, how the storage exactly works. So, if you want to get more details on how we turn block storage into object storage, you can read it there. And that's kind of the next steps. And the really ultimate step is, of course, if you would join us in OpenStack Paris. It's about 3 hours driving from here, but I guess for most of the US people it will be a long trip. But it's on November 3 till 7. It's in Paris. We will be there. We will not be branding us with the OpenVStorage booth, so we will not have an OpenVStorage booth. We have there the booth of the mother company, CloudFounders. So that's the company I work for. That's the company that all the core engineers are working for. So that's kind of how we are there. So on this last slide, I would like to finish. So Rafael, feel free to now jump in, ask questions.
Yes, thank you very much for the presentation, Wim. Oh, sorry, Stephen, go ahead.
I was going to try. Wim, can you hear me okay? I was going to try to ask some questions. Hopefully my microphone's working better.
Yeah, I can hear you.
Okay, so I do want to tell you, Wim, you did a great job, and it's the largest discussion we've ever had on IRC, so there's certainly a lot of interest in this. So I'm going to go through a couple of questions. The first one was, you talked about the S API at the beginning. Are you using the native Swift API, or is this an S3 translation API?
We use the S3 API.
Okay. And the second question.
Stephen, I just want to note on that we could use the Swift the Swift one, but S3 is such a common thing. It's much easier to do it like that. That's our opinion.
Okay. The next question was talking about, you showed in one of your diagrams that you had 40K IOPS.
Yes.
Can you provide details on how you got that number?
Yes, we can provide details on that. It's done with Fusion IO cards, but I don't have the numbers here. But if the person reaches out to me, then I can provide them the numbers very easily. I don't have them here right now, so. But if the person out there reaches out to wim@openvstorage.com, I will be more than glad to provide them the details about how we did this.
It was John D. But it might be something good for you guys, maybe to put in a blog or something, because it's a good number. It'd be an interesting blog.
Yeah. We are actively working on getting those numbers out.
Okay.
We are, for example, also we get a lot of questions of people. Okay, I already have a Ceph. is it worth putting you in front of Ceph? And there's various reasons why it would be worth putting us in front of Ceph. And one would be, for example, because it gives you a better performance. For example, it gives you also the possibility to add VMware. But that's something we're working on. It's as you know, IOPS is a very difficult thing to quantify, and there's always a lot of testing going on about how to set it up, discussing the setup, making sure that it's performant enough, because we don't want to offend people from Ceph, because Ceph is a great backend for us, just like Swift is a great backend for us. But it just takes time to get these numbers out there.
No problem. So we have a few more questions. Someone says, is this write-back caching? If KVM1 failed, would I lose data that hasn't been committed?
No, you don't lose data which hasn't been committed. So every write that happens to one host is also copied or synced to a different host, where we have a synchronized distributed transaction log. That's how we call it. So it's a copy of one write is also on the other host. And if the first host dies, you still have the data on the second host. And if the volume gets back, you can just you just have the data of that transaction log on the different node. So if a host goes down, there's no data loss. Okay.
So we got a few more questions. This is great. Everyone with the questions, I'm really excited. Raphael and I have been trying to get questions for these things. This is great. Someone wrote, what's the comparative performance of using vStorage with Swift as opposed to other Cinder block drivers?
I don't have any idea, to be honest. We haven't had that question. Well, we didn't have that question, so I don't have an answer for that.
Okay.
The only thing I would say is if you have your OpenStack right there, you already have a Cinder, just give it a try. We're open source, we can't do everything, so we could use some help on those numbers if you have them.
Okay, good. The next question was, how does this compare to, this is something I haven't heard of, S3MPER from Netflix?
I haven't heard of it also, so I will, if the person, if you can write down the names of the person that asked that question, we'd be more than happy to answer that in person.
Okay.
But I have no idea about S3, whatever it was from Netflix.
Okay, and then we have what KVM management utils is this compatible with? And someone wrote Overt, or is it something else?
I think it uses Overt underneath. So it uses OpenStack, which has, I think, Overt underneath it, so that you can that you can use it. Basically, calls Overt libraries just make the calls, and that's how it works. Does that answer the question?
Yeah, it's good. No one else has chimed back that they didn't like it. So I think the last one we'll go with is, how important is RAID mirroring for the SSDs and the hypervisors themselves?
Is that a general question or a question for us?
This is a question I see. I'm just reading questions, so
okay.
You can yell at me all you want. I'll be the the delivery of the questions. I'm not. The question confuses me, so.
Well, I think the question that people are asking is, what are the chances that an SSD fails? Well, the chances are very big that it will fail if you do lots of writes in case you don't use an enterprise-grade SSD. So if you want to use Open vStorage, please make sure that you have an enterprise SSD for the write cache. You can split up write cache and read cache. SSDs for the read cache can be cheaper disks because they don't have to endure. They don't get as many writes as the write SSDs. But if you have to really have an enterprise write SSD for the caching, especially for the write caching, or a PCI flash card. Now we have not seen, and we have we've been doing this kind of thing for, let's now say, 4 years. We've learned it the hard way that desktop SSDs don't work, and we have now, for example, for a commercial product, we only ship it with Fusion IO cards, the IO scale cards, and we have never had a problem with that. So the really enterprise SSDs or Fusion IO or PCI flash cards are really, really good. These are really almost indestructible. If it would fail, you still have your data, as discussed previously, on another host, so there's no data loss. It just will take some time to reboot that virtual machine and get it up again on the second node.
All right. So, Wim, thank you very much for your presentation and for asking all those questions that were coming in. And thank you all guys who are attending us. Thank you for the lively discussion that we had at IRC.
Okay.
Thank you, Stephen, for co-hosting.
I'm looking forward to see it because I couldn't see it. So I'm looking really forward to see what all the questions were and if I really did a good job. So.
You really did. You really did. So thank you very much, everybody, and see you next time.
Okay. Bye-bye.